Hi everyone, in this video we're going to be talking about linear independence, and this is going to be for vectors, and then we're going to expand that to matrices. So let's start with this definition. An index set of vectors, we're going to say it's the set containing vectors v1, v2, all the way to vp in Rn, is said to be linearly independent if you have this vector equation, and the only solution to this equation is called the trivial solution. So what that means is the vector 0. Okay, so if x1, x2, all the way to xp is a column vector, then what we're saying for linear independence is that that has to equal 0 for this to be considered linearly independent. But notice this is only when we're looking at the case when this equation equals 0. Okay, and so the set of vectors is called linearly independent if the only way to get this linear combination of x1 times v1 plus x2 times v2 and so on to equal 0 is if all these x's were actually 0. All right, now the opposite of that is linearly dependent vectors. So the set containing the vectors v1, v2, all the way to vp is linearly dependent if there exists weights, which we're going to call c1 to cp, that not all of them are 0. So some can be 0, all but one can be 0, none can be 0, but as long as not all of them are 0, then when we have this linear combination here and the result is 0, then this is considered linearly dependent. Okay, so these are opposites of each other, linearly dependent and independent. And so our second equation, the dependent one, we call that a linear dependence relation among those vectors. And this is true when the weights are not all 0. So an indexed set is considered linearly dependent if and only if it's not linearly independent. So the fact that these are just opposites is this bullet point. All right, so let's take a look at this example. We're going to have our vector v1 be the column vector containing 1, 2, and 3. v2 is going to be the vector 4, 5, 6, and v3 is 2, 1, 0. All right, so we want to determine two things. Is the set of those three vectors, v1, v2, v3, linearly dependent? And then b, if possible, find a linear dependence relation among those vectors. Okay, so starting with figuring out, are they linearly independent vectors? So we have to first determine if there's a non-trivial solution to our linear combination equation. So remember what our definition was. For linear independence, we had our vector equation. It was x1 times v1 plus x2 times v2, in this case plus x3 times v3 equals 0. And as long as we get an answer for x1, x2, and x3 that's not trivial, not 0, 0, 0, then we can say yes, these are linearly independent. So we're using the definition to determine if this set is linearly independent. All right, so in order to do this, we're going to do our row operations on the augmented matrix associated with our vector equation. So our vector equation, notice this is column 1 here of this matrix is from vector v1. This was vector v2, and this is vector v3, and this is the other side of the equal sign. We're saying, does this equal 0? And so let me just write down the vector equation for this really fast. Okay, so here's our vector equation. I mentioned it in the previous slide, but I just want to make sure you understand. So this is the equation in vector form, but then we translate it to an augmented matrix. So this is the matrix version of the same equation. Okay, and so you don't see the x's because they represent the columns. So the column 1 is the coefficients which came from v1, but it's the coefficients on the variable x1, okay? And then column 2 is the coefficients from v2 on your variable x2, and so on. And then the other side of the equal sign is the vector 0, 0, 0. Okay. All right, so if we do some elementary row operations, we get to this equivalent matrix. And let me just remind you, we've done this in the past, but I want to make sure you're good with doing your row operations. So notice this is a pivot in row 1, column 1. So we want there to be zeros below it. So think about what you would do to get this 0 in row 2 and this 0 in row 3, and then I'll write it down right after this. Okay, so hopefully this is what you were thinking about. If we do -2 times row 1 and we add it to row 2, that's how we would get a 0 right here in column 1. And then it would become -8 plus 5, that's where -3 came from. That would become -4 plus 1, also -3. And then it would just be 0 plus 0. And then for row 3, we actually would have to do this in 2 steps. So the first step would be -3 times row 1, and we would add that result to row 3. That will be our new row 3. And then we'd have to do one more step. So let me just show you what you would get in between here. Okay, so then this would be your in-between step. I just did row 3 to show you what you would get when you replaced it. And then from here, notice what you could use. You could use your new row 2, and you could say something like -2 times row 2, and you can add that to row 3, and then that's how you can get that new row 3 where it's all zeros. Okay, so just a reminder of how to do some of your elementary row operations. All right, so notice what we have based on this reduced form here. We have x1 and x2 are basic variables because we have pivots in those columns, in x1 column, x2 column. But x3 is free, it's a free variable because there's no way to get a pivot in column 3. And so x3 is a free variable. And so any non-zero value we choose for x3, then we're going to get a non-trivial solution to our first equation. And so remember, to be linearly independent, we could only have the trivial solution to that first equation, that vector equation. And so right here we see that any value that's not 0 for x3 will give us a non-trivial solution. Therefore, our vectors are linearly dependent. Okay, so now let's find a linear dependence relation among those 3 vectors. And so if you just keep doing your elementary row operations on your augmented matrix, so that notice this is your reduced form, we can't simplify it any further. And so if you translate this to equations, you have, this says x1 minus 2x3 equals 0, that's equation 1. And this says 1x2 plus 1x3 equals 0. And then the last row just says 0 equals 0, which is a true statement. So remember, this is going to give us infinitely many solutions to this system. And then there's lots of ways to write this, if you recall. One of the things you can do is solve for your basic variables in terms of your free variable. So we could say something like x1 equals 2x3 and x2 equals negative x3, but it's the same system. Okay, so x1 equals 2x3, x2 equals negative x3, and then x3 is our choice, it's free. So if we choose any value for x3, as long as it's not 0, then we can go forward. Let's say x3 is 5, then plugging that into our other 2 equations, we're going to get that x1 is 10 and x2 is negative 5. And so if we put these values into our original equation, our vector equation, where it was x1 v1 plus x2 v2 plus x3 v3 equals 0, then we have this equation below. And this is one out of infinitely many linear dependence relations that you could come up with among these vectors, v1, v2, and v3. Okay, so now we're going to transition from linear independent vectors and just expand that to linear independence of matrix columns. So for matrix A, remember the vectors just make up the columns. So now we're just putting those vectors together in a matrix and calling that matrix A. So same ideas, we're just looking at a matrix now. So the matrix equation, AX equals 0, is exactly our equation we've been looking at for linear independent and dependent vectors. And then each linear dependence relation among the columns of A, which is just our vectors, A1, A2, and so on, corresponds to a non-trivial solution of AX equals 0. So this is exactly our same definition for linear dependence as we had for our vectors, but A is just a matrix of column vectors. And then the columns of matrix A are linearly independent. And remember, this is going to go along with our definition we already looked at. If and only if our equation AX equals 0 has the trivial solution as its only solution. So same definition that we just looked at earlier, but we're now just relating it to our matrix, which its columns are made up of our vectors. Okay, so now let's discuss sets of one vector, and then we'll start moving up to two vectors and so on. So a set containing only one vector, let's say it's the vector v, you can figure out if it's a linearly independent vector if and only if it's not the zero vector. So if you only have one vector, it's linearly independent as long as it's not zero. And the reason for this is because if you look at this vector equation, x1 times that vector v has to equal 0. And that's true as long as v is not 0. So if v is not 0, then this equation is not going to equal 0 unless x is 0. And then if x is 0, that's exactly the trivial solution by definition. Okay? So linearly independent vector as long as it's not 0. If it is 0, if it is the 0 vector, then it's considered linearly dependent. And that's because, notice if we just take the same equation, but now we're saying v is 0, it's a 0 vector, then anything you choose for x, it's going to be something times 0 equals 0. And so it has a bunch of non-trivial solutions, and so it's linearly dependent if it's a 0 vector. Okay, so now that's for one vector. Let's move up to two. So sets of two vectors, we'll say the set containing v1 and v2. A set with two vectors is linearly dependent if at least one of the vectors is a multiple of the other. So that's really easy to tell. Usually you can just divide them, like divide v1 by v2. And if for every entry you get the same constant, then they're multiples of each other. So for example, I'll just do a super easy one. Okay, so take a look at this. This v1 is the vector 1, 2, and v2 is the vector negative 4, 8. You can tell in this one just by looking that if you times v1 by negative 4, you're going to get v2. If you can't tell by looking, you can divide, and it doesn't matter which way you divide. If we said v1 divided by v2, we would just get negative 1/4 as the factor between them, and that would be the same for the second row as well. 2 over negative 8 is still negative 1/4. So that's when they're linearly dependent, if one of them is a multiple of the other. And so the exact opposite of that is independent. The set of two vectors is linearly independent if and only if neither of the vectors is a multiple of each other. Okay, so now let's move up to two or more vectors. So we have a theorem for this, and we're going to characterize our linearly dependent sets. Okay, so what this theorem says is if you have a set of vectors where there's at least two, so two or more vectors, and if we know that that set of vectors is linearly dependent, then that's because it's only true if and only if at least one of the vectors in the set is a linear combination of the others. Okay, so a set of vectors is linearly dependent if one of the vectors is a linear combination, or you can kind of think of that like a multiple of the others, or at least some of the others. So in fact, S is linearly dependent and vector v1 is not 0, then for some vector, we'll say greater than v sub 1, is a linear combination of the preceding vectors. Alright, so I'm going to walk you through the proof for this theorem. You don't have to get caught up on the proof, but I do just want to show it to you. So just try to track with me. Okay, so first we're going to address this one direction and then kind of go the other way. So we're going to try to show that for some vector in our set, it's a linear combination of the other vectors, and then therefore we can claim it's linearly dependent, and then we'll go the other direction. Well, we'll start with linearly dependent as the given, and then we'll show that we have one of the vectors as a linear combination of the others. So we're kind of doing it two directions here. All right, so for v sub j, as one of your vectors in your set, it's a linear combination of the other vectors, and then it can be subtracted from both sides of an equation, producing a linear dependence relation with a non-zero weight, in this case of -1 on v1. So it sounds a little wordy, but just take a look at this here. So kind of just assume, and it could be any combination, but let's say v1 is just some scalar or weight c2 times v2 plus c3 times v3. And this set can have many vectors in it. It doesn't just have 3, just so you're aware. Notice there's no v1 here, It's over here actually. There's no v4, v5, v6, but it could go up to a lot of vectors. So then if you move this v1 over by subtracting, we would get this equation here. And look what we have. We have 0 equals negative 1 times v1 plus c2 times v2, which was here, plus c3 times v3, which was here. And then if there's more vectors, it would just be 0 times those vectors. So this is a linear combination of the vectors in the set. One of our vectors in the set equaled this linear combination. And so because this is a linear dependence relationship with at least this one non-zero weight on v1, then our set is linearly dependent. So now the other direction, let's say that S is linearly dependent, and then we want to show that we can write one of our vectors as a linear combination of the others. So we have a couple of cases here. If v1 is 0, then this one's done because it's just a trivial linear combination of the other vectors. So we more so want to get into if it's not 0. So this is the remainder of the proof. Again, don't get caught up on this too much. I just want to show it to you. And so if this vector is not the 0 vector, then we say there exists some weights, c1, c2, and so on, that not all of them are 0, such that they satisfy this linear dependence relation right here. And so we're just going to say that j is the largest subscript for which c sub j is not 0. And so let's say j is 1. Then c1 times vector v1 equals 0 is impossible because we already said v1 is not 0, and we just said c1 is not 0. Okay, so that's a sub case here. And so we say, well, then j has to be more than 1. And so in that case, we have c1 times v1 plus c2 times v2 and so on, plus j times vj, and then everything beyond that is 0 times our vector plus 0 times our vector and so on. And so we can write this as some vector cj vj equals, so if you bring these all over, negative c1 v1 minus, it would be c2 v2 and so on, all the way to right before cj vj, right, the term right before this, we would stop there. And those are all the ones we would bring over to the other side of the equal sign. And so the point of this is to show you now, you can get your vector vj by dividing out cj. And so notice what you have. You're going to have a linear combination where vj equals a linear combination of the other vectors. Okay, so that's the proof of that theorem, but more so we just want to know what the theorem states. You don't really have to prove it, just know what it states so that you can use it. Okay, so notice what it does not say. The theorem did not say that every vector in a linearly dependent set is a linear combination of the preceding vectors. It said that at least one of the vectors, not every, is linear in the set is a linear combination of the others. So a vector in a linear dependent set, it actually might fail to be a linear combination of the others. So let's take a look at this example. Let the vector u be 3, 1, and 0, and then the vector v have entries 1, 6, 0. And we're going to describe the set spanned by these two vectors, and then explain why a vector w in the span of these two vectors is in that set if and only if u, v, and w are linearly dependent, the set containing them. Okay, so first we'll describe the set spanned by u and v, and then notice that this explain part, it's an if and only if, so we have to do that two directions. We have to say that if w is in the span of uv, then we have to show that the set is linearly dependent. Then we have to go the other way and say that if the set is linearly dependent, then w's in the span of uv. Okay, so first, the vectors u and v are linearly independent if you go look at them, because neither one of them was a multiple of the other. And so they span a plane, a 2D plane in R3. They're in R3 because there's 3 entries in those vectors, but it's a plane that they span because there's only 2 vectors, and so you can do any linear combination of them, and that's the result of span of uv. So if you want to think of it like the x and y plane in 3D space, that's one way to think about it, but we're going to call it the x1, x2 plane, and then x3, the third variable, would be 0. Okay, so that's the description of the span of u and v. So remember, this is a set. We talked about the span in the past. It's just a linear combination of all the vectors in the set. Okay, so now let's look at W. If W is a linear combination of U and V, meaning you could say something times U plus something times V equals W. So if we know that's true, then the set containing U, V, and W is linearly dependent by our theorem that we already proved. So now that we've proved that theorem, we can use it. So we can say by that theorem, then the set's linearly dependent. And now the other direction, suppose that the set is linearly dependent to start with, can we show that W is a linear combination of U and V? Okay, so by the same theorem, we know that some vector in this set is a linear combination of the other vectors. And then we know that U is not 0 and V is not 0. That was given. And so that vector must be W, since V is not a multiple of U. So because U and V were linearly independent, we know that V is not something times U. And so out of these three vectors, one of them is a linear combination of the others, and it's got to be W. Okay, so W is in the span of UV. So we just proved what we were asked to explain. And so two images for you here. When we have our linearly dependent set, W is in the span of U and V. So notice what you have. You have a plane in 3D space, but it's a 2D plane. And then this plane, this blue plane, would be created by all the linear combinations of U and V, and W's in that plane, somewhere in that plane. If the set was linearly independent, then what would happen visually is that you would have this plane that's the span of UV, but W would not be in the plane. It would exist somewhere else outside of that plane. So the example that we just looked at generalizes to any set containing our three vectors in R3, where two of them are linearly independent. And then the set U, V, and W will be linearly dependent if and only if W is in the plane spanned by U and V. So this is just sort of generalizing but restating what we've already shown. W is in our plane spanned by UV, which is, by definition, the span of UV, and it was because the set was linearly dependent. Okay, so a couple more theorems for us. This theorem says if a set contains more vectors than there are entries in each vector, then the set is automatically linearly dependent. So another way to say that is if you have your set, V1, V2, V3, all the way to Vp, vectors in Rn, it's linearly dependent if P is greater than N. Okay, so look at what P and N are. P is going to be your amount of vectors in that set. So let's just say this set had 5 vectors in it. So P would be 5. Now the number of entries in each vector is the letter we've been saying is N. So if, let's say each entry had, there's 4 entries in each vector. So like there was a vector, it had 1, 2, 3, 4 in it, and then so on. Then if P is greater than N, in my example I just said, 5 would be greater than 4. It's automatically a linearly dependent set. So it's kind of a fast way to just be able to tell if your set is linearly dependent. Okay, so here's just a quick proof for it. Let A be our matrix containing those vectors. Then A is size N times P, because the number of rows would be based on the entries of each of these vectors, which we already know from back here. Each vector has N entries, so N rows, and then there's P amount of vectors, so the columns is P. So then A is an N by P matrix, and then our equation, our matrix equation, AX equals 0, corresponds to a system of equations of where we have N equations, and then there's P unknowns. And so if we keep going with this information, we would say that, so if P is more than N, that really translates to there being more variables than there are equations. And so there must be a free variable, and therefore the set is linearly dependent. So hence, AX equals 0 has a non-trivial solution, and the columns of A are linearly dependent. So here's a matrix version of what this theorem is saying. Anytime P is greater than N, so notice your columns, your amount of columns or your vectors is more than the entries, so in this case it's 5 columns or 5 vectors and 3 entries each, then we have linearly dependent vectors. And so just a quick note, this theorem, what it doesn't say anything about when p is less than n. This is only having to do with p is greater than n, then we know that the vectors are linearly dependent. So our last theorem here says, if our set of vectors in Rn contains a 0 vector, then the set is also automatically dependent. So another way to quickly tell if we have a linearly dependent set. So if you have a set of vectors, no matter what's in there, but if you see the 0 vector, you can just say that this is a linearly dependent set. So quick proof. By renumbering the vectors, you can just say that the first one is the 0 vector. So then we would have the equation 1v1 plus 0v2 and so on equals 0. And then notice what this says. It says 1v1 equals 0, but we're already saying that v1 is the 0 vector. And so this is a non-trivial solution to our matrix equation. 1 times the 0 vector equals 0, where 1 being the non-trivial solution. And so this set is linearly dependent. So these last two theorems are just some fast ways to tell if your set of vectors is considered linearly dependent. All right, so that's it for talking about linearly independent sets and our linear independence when it comes to vectors and our matrix full of column vectors. All right, that's it. Thanks for watching.